In section 11.4, we look at the topic of colligative properties. There are 4 colligative properties that we'll be looking at: vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. Then we'll look at how colligative properties can be used to determine the molar mass of a solute. So the first colligative property that we're going to be looking at is called vapor pressure lowering. So, just recapping on what we mean by a vapor, the particles that escape a liquid and enter the gas phase at a temperature lower than the normal boiling point are referred to as the liquid's vapor. So, how we determine the vapor pressure of a liquid is we take our liquid and we put it into a sealed container and we wait for the physical equilibrium between the liquid and the vapor to occur. And you can tell when you've got to this point because the level of the liquid will stop changing. The pressure that we measure above here at that point in time is called the vapor pressure. Some properties of the vapor pressure that are important to realize is that the vapor pressure of a liquid decreases as attractive forces or intermolecular forces between the particles increase. So, the stronger the intermolecular forces, the lower the vapor pressure. Volatile substances are liquids that have relatively low intermolecular forces and therefore have high vapor pressure. The vapor pressure will be dependent upon a liquid's temperature because as the temperature increases, the average kinetic energy of the particles increase and the more likely they are to be found in the gas phase. It's important to realize that evaporation will occur faster when the surface area of a liquid is increased. And this makes sense because evaporation can only occur from the liquid. So if we bring more particles can only occur from the liquid, can only occur from the surface. So if we increase the number of particles that are at the surface, we'll increase the likelihood of the vapor forming. So all of that put together means that when we have more surface area, evaporation occurs more quickly. So if we consider 2 containers containing a liquid that have the same surface area, but to one of these samples we add a non-volatile solute, what we can see happens is that the non-volatile solute will occupy some of the surface positions, and as a result, that will lower the vapor pressure of our liquid. And so this phenomena is called vapor pressure lowering. And obviously you can see that as the concentration of our non-volatile solute goes up, the vapor pressure lowering effect will increase. So this is a property that depends upon the concentration but not the identity of the non-volatile solute. So vapor pressure lowering is described quantitatively by a rule called Raoult's law. And Raoult's law just simply says that the pressure of our solution is equal to the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent. So just recapping what we mean by mole fraction, the mole fraction of the solvent is the number of moles of the solvent divided by the total number of moles that are in our solution. That is the number of moles of solvent plus the number of moles of solute. And you'll know if you're calculating this correctly because it'll always be a number less than 1 because the solution is not entirely solvent. So this works well with our formula, doesn't it? The pressure of our solution will always be less than the pressure of our pure solvent because we're always going to be multiplying by a number that is less than 1. So these tend to be just kind of plug and chug type problems where you're solving for one of the unknown variables in your equation. So this problem reads, the vapor pressure of pure water at 20 degrees Celsius is 0.0231 atm. If 17.95 moles of ethylene glycol is dissolved in 55.49 moles of water, what would be the vapor pressure of this solution at 20 degrees Celsius? So let's just write out Raoult's law. It says that the pressure of the solution is equal to the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent. So the mole fraction of our solvent is simply the moles of solvent, which is the moles of water, divided by the total number of moles, which is our moles of solvent, plus our moles of solute, which is the ethylene glycol. And then we have to multiply that by the vapor pressure of the pure solvent, which we're told in the opening sentence is 0.0231 atm. So putting all of that together gives us a vapor pressure for this solution of 0.0175 atm, which is less than 0.0231. So this looks like it makes a lot of sense. Now, there's a little bit of a complication here, which is that Raoult's law is derived assuming that the strength of solute-solvent interactions are the same strength as solvent-solvent interactions. This is what we call an ideal solution. So what we're really saying is that these little red guys on the surface here and dispersed throughout don't hold back the green solvent molecules any more or any less than the solvent molecules themselves. Now, if that wasn't the case, then we'd have a bit of an issue, wouldn't we, right? So say that the interactions between these guys and the green guys were really strong, then that would lower the vapor pressure, right, even further. But if they were really weak, then replacing some of the forces that are holding the green guys into the liquid phase with a weaker interaction, well, that would increase the vapor pressure. So what we're saying is this: if the solute-solvent interactions are greater than the solvent-solvent interactions, the vapor pressure will be even lower than predicted by Raoult's law. However, if the solute-solvent interactions are less than the solvent-solvent interactions, then the vapor pressure will be greater than predicted by Raoult's law. So that's kind of cool. You could calculate what you expect using Raoult's law, and then you could measure the actual vapor pressure, and you can tell the relative strength of these intermolecular forces. So, vapor pressure lowering, as described by Raoult's law, is an example of what we call a colligative property of a solution. And what makes a colligative property is that it depends only on the number of solute particles, but not their identity. So we can see that here, the mole fraction is only about the number of particles. Nowhere do you identify the identity of the particles. So we don't have a term in here for the that in any way expresses the identity of things. It doesn't matter the identity. It only depends on the amounts. So that concludes the part of 11.4 that's concerned with vapor pressure lowering. So now we move on to our next colligative property, and what we're going to talk about now is freezing point depression and boiling point elevation. And these two colligative properties tend to get talked about together because they have very similar formulas describing how they operate. So the first complication that we have when we begin to talk about changes in temperature is that the volume of a solution is observed to change with temperature. So you've probably heard of pipes perhaps freeze bursting in winter. And this is a result of the fact that when aqueous solutions get cooled below about 4 degrees Celsius, they start expanding. And if they expand enough, you can actually burst your pipes. So when we're looking at properties of solutions where the temperature is changing, we have a problem because we're going to need a measure of concentration that is independent of temperature and in particular doesn't depend on volume. So molarity is not going to work for us because molarity is the moles of solute over the volume of the solution. And as volume depends on temperature, then so will molarity. So when we're talking about freezing point depression and boiling point elevation, we're going to be using molality, which is normally given the symbol lowercase m, as our unit of concentration. And the reason for this is because molarity is given by the moles of solute divided by the kilograms of solvent, and neither of these two quantities varies with temperature. The number of particles doesn't change with temperature, neither does the mass of the system. So we're just going to recap what we mean by the boiling point. So the boiling point of a liquid is defined as the temperature when the vapor pressure equals the external pressure. And you can recognize that something is boiling because you'll see bubbles of the vapor forming near the surface of the liquid. And you kind of recognize that. And the reason that this can happen is because the bubbles contain the your liquid in the gaseous form at a pressure equal to or greater than the external pressure. So they just simply won't just get crushed, they'll actually form and rise to the surface. So bubbling is an indication that you have obtained boiling. So as we described earlier, adding a solute to a solvent decreases the vapor pressure at any given temperature. So as a result, the temperature required to reach atmospheric pressure to reach the normal boiling point is going to be increased in the presence of a non-volatile solute, right? So say it was at boiling, 760 torr, and then you add a solute, well, that's going to decrease the vapor pressure and kill the boiling. So the presence of a solute results in an increase in the boiling point of a solution compared to the pure liquid. So it turns out that boiling point elevation is a colligative property. It's described by this equation. The change in the boiling point is equal to a constant, which is called the boiling point elevation constant, and that's characteristic of the particular liquid that we're interested in, the particular solvent, multiplied by the molality of our solution. And I put a little note here that says we must take into account the total number of particles. And that's important for solutions of ionic compounds. So say we have sodium chloride at a concentration of 1 mole per kilogram. We need to be mindful that when sodium chloride is dissolved in water, it forms 2 particles. So that means we actually have a molality of total particles of 2 moles per kilogram. So you need to be a little bit careful there when we have ionic solutes. So this problem illustrates how we use the boiling point elevation equation. So it reads, the Kb of water is 0.52 degrees Celsius per mole. What is the boiling point of seawater if the concentration of ions is 1.15 mole? So I just begin here by writing the equation. And I realize that I have everything I need to calculate the change in the boiling point. I have the boiling point elevation constant for pure water, and I have the molality of all of the ions. So I multiply those two together and I see that seawater has a boiling point that is 0.598 degrees Celsius higher than pure water. So I'm just going to add this to the boiling point of pure water to get the new boiling point of our seawater, which is 100.598 degrees Celsius. So seawater boils a little hotter than fresh water. If we look at the phase diagram for a pure solvent and then also a solution, what we'll observe in each case is a depression of the freezing point. So here's a good example. We're looking at the freezing point of an aqueous solution versus the freezing point of pure water. And the we can see that we've got to find the line that separates the solid and the liquid, and we can see that in the case of the pure water, here it is here's the line, that the freezing point is greater than the position of the same line for the solution. And that is always the case. So freezing point gets depressed, whereas boiling point gets elevated. The good news is that this is really helpful for us because we can use this to stop solutions to stop solvents from freezing when it gets cold. For example, if we have a wet road and we put salt on it, well, we're going to be able to lower the freezing point of the water and perhaps prevent it from freezing overnight. And so it's kind of interesting. Sometimes you'll see coolant, radiator coolant, sold also as antifreeze. And that kind of makes sense because any solute will both lower the freezing point and raise the boiling point. So anything that stops your radiator from freezing will also stop your radiator from boiling. And so really how you choose to market these things just depends on whether a motorist is more likely to have their car overheat or freeze up. So freezing point depression is also a colligative property, just like vapor pressure lowering and boiling point elevation. And the nice thing is it's described by an equation that is very similar to the boiling point elevation equation. In particular, we observe that the change in freezing point is equal to a constant characteristic of our solvent called the freezing point depression constant multiplied by the molality of our solution. So the kind of math that we'll be doing was just like what we illustrated before when we had the boiling point elevation problem. Something I want to come back to is discussing the impact of dissociation on how we calculate the molality. So when a non-electrolyte is dissolved in water, for every mole of solute dissolved, we get 1 mole of particles. So if I take the covalent compound methanol and dissolve it in water, for every mole of methanol, I end up with 1 mole of aqueous methanol. I end up with 1 particle. However, when an electrolyte, such as an acid or an ionic compound, is dissolved in water, we will always obtain more solute particles than the moles of solute dissolved. So for example, if I dissolve sodium chloride solid into water, for every mole of sodium chloride, I'm going to get 2 moles of solute particles, 1 mole of sodium ions and 1 mole of chloride ions. So we have to take this into account and make sure that we accurately express the molality. So one way of helping us with this is the Van Hoff factor. It's normally given the symbol I, and this is defined technically as the ratio of experimental value of a colligative property to the value calculated if the solute was a non-electrolyte. So that's quite a mouthful, but I think a more simple way of understanding what the Van Hoff factor or the I factor is that it is 1 for non-electrolytes, and then it is the number of moles of ions formed when an ionic solute dissolves. So, if you are told that your solute is a non-electrolyte, that immediately is telling you that I equals 1. However, if you are told that it is an ionic compound, a strong acid, or some other way you're told that it is an electrolyte, then you'll need to consider the number of moles of ions that are formed when it is dissolved in water. Now, what we can do now is we can modify our previous equations for freezing point depression and boiling point elevation to include the Van Hoff factor. So there we are, we're just going to put them out the front there. And so just recapping, this Van Hoff factor expresses the extent to which free ions form when the electrolyte dissolves. So if we have something like this, then our I would equal 3 because we get 3 of these guys for every one of those guys. So we have to be a little bit careful. Now, if we have something like this, we will also get a Van Hoff factor of 3. Okay, so just keep that in mind. Now, a complication that can occur is that at high concentration, sometimes oppositely charged ions will attract one another and form what we call ion pairs. Now, this is only going to happen at high concentration when it's likely that opposite charged particles are going to sort of accidentally bump into each other. Now, if that happens, the extent of dissociation might be less than what we would predict by just considering the formula. So, for example, in a 0.01 molar sodium chloride solution, we see negligible ion pairing, and as we might expect for sodium chloride, I is 2. However, if we bump the concentration up to 1.9 molar sodium chloride, then we start seeing some ion pairs forming as a result of the high concentration, and I will actually end up being a little less than 2. So if we are reading a problem and they are talking about complete dissociation, or they say assume complete dissociation, then that's really telling you that you can figure out I on the basis of the formula. Okay, so that concludes the section on freezing point depression and boiling point elevation. These are both colligative properties that have very similar equations. We do need to be mindful when we are working with these colligative properties to work with concentration in terms of molality rather than molarity. The final colligative property that we will look at is one known as osmotic pressure. So osmosis is the process by which a solvent will move across a semi-permeable membrane separating two solutions of different concentrations. And perhaps the most famous of semi-permeable membranes are things like cell membranes. So the membrane that separates the nucleus of a cell from the rest of the cell, or perhaps the membrane that separates the cell from the outside world, so the cell wall. And these membranes are described as being semi-permeable because they allow some things to move across, but not other things. In this case, the semi-permeable membrane that we're talking about will allow solvent to move, but not any solute particles. So what happens is, if we have a solution with a high concentration of solutes separated from a solution with a low concentration of solute, then solvent will move across the membrane to try to lower the concentration on the high side and to try and raise the concentration on the low side. The solvent will continue to move until the two concentrations are equal. Now, this has some kind of interesting consequences. It is because of osmosis that it's essential that when we administer a solution intravenously, that the solution is isotonic with respect to the concentration of the contents of our cells. So when we put something like a red blood cell in an isotonic solution, that is one where the solute concentration is matched to the solute concentration inside the cell, then the rate at which solvent, water, moves across the cell membrane is the same in both directions. That is, water does not either rush out of the cell nor rush into the cell to attempt to equalize the concentrations. However, if we put our cells into a hypertonic solution, that is one where the concentration outside the cell is really high, then what happens is water will rush out of the cell across the semipermeable membrane to try to lower the concentration out here and raise the concentration within the cell until they are matching, and you end up kind of basically dehydrating your cell. Now, if you have what they call a hypotonic solution, and that is where the concentration out here outside our cell is much lower than the concentration inside the cell, then what will happen is water will rush across the semipermeable membrane into your cell, and the cell will swell up, but it will lower the concentration of solutes inside your cell and raise the concentration of solutes outside the cell until they are equal. But what happens most of the time is that the cell becomes unstable and dies before we kind of end up with equal concentrations on both sides of the membrane. So, what has this got to do with osmotic pressure? So, here we have a high concentration of solutes, a low concentration of solutes. So we know that solvent is going to move right to left in order to equalize the two concentrations. Once the concentration is the same on either side, the rate of movement of solvent across the semipermeable membrane will be the same in each direction, and so the concentrations will just stay equal. What we're interested in is this thing called the osmotic pressure, which, to distinguish it from the pressure of a gas, rather than giving it the symbol P, they give it the Greek symbol for P, which is pi, and that pressure is the pressure that is required to stop the movement of solvent across the membrane. So basically, it's the pressure that we would have to apply here to make sure that there's no movement of solvent in this system. So how much of a force would we have to apply to stop the movement of solvent? So it turns out that the osmotic pressure is a colligative property. That is, it only depends upon the concentration of our solute. And the osmotic pressure is given by this formula. So it says pi, the osmotic pressure, is equal to the Van Hoff factor multiplied by the difference in molarity of solutions, multiplied by the ideal gas constant, multiplied by the temperature of our two solutions. Now, something to be mindful of, if they don't mention a second solution, you should assume that they are measuring the osmotic pressure against the pure solvent that is that the molarity of our second solution is equal to 0. And often the questions are not well worded and don't make that super clear. So here's an example problem. It says a typical red blood cell has a concentration of solutes of 0.3 mole per liter. Calculate the osmotic pressure across a red blood cell if it is bathed in pure water at 25 degrees Celsius. So, because they just said the concentration of solutes, rather than talking about electrolytes and non-electrolytes and complete dissociation and all of those things, we're going to assume that we don't need to take into account the Van Hoff factor, and that the concentration 0.3 here represents everything in solution completely dissociated. So for that reason, I've put 1 in here as the Van Hoff factor. Now, the difference in the molarity of our solutions, 1, the red blood cell has 0.3, so that's one of our concentrations, and then we're putting them in pure water, so that has a concentration of solute of 0. So the difference in molarities there is going to be 0.3 moles per liter. Here is R. We need to be mindful to use the correct value. We're looking to solve for a pressure, so we need the units of R to have ATM in them, because that's a unit of pressure, so we make sure that we have that. And then lastly, we have to multiply by the temperature, and considering the units for R lets us know that the temperature must be in Kelvin, so we have to turn our 25 degrees Celsius into Kelvin. So if we do all of that, and then we check our units, we see that what we have are units for ATM. So 7.3 ATM is the pressure. So 7 times atmospheric pressure. And doing a little bit of math here, 1 ATM is a little over 14 psi. So 7 times 14 gives me 98 psi. So that's about 3 times the pressure in your car tires. So it's not really good for little red blood cells to get pumped up like that. That's going to cause a big issue, and that's why you can't inject large volumes of pure water into somebody. So what's going to happen in this case? Because the concentration of solutes is much greater inside the cell than it is outside the cell, water is going to go rushing into the cell to try and dilute down the concentration inside, and that's going to result in our cells swelling up. They're going to get pumped up with about 100 psi pressure, and they're probably not going to survive that. And if you did this on a large scale, somebody would probably get quite sick. Okay, here's another one. It says calculate the osmotic pressure across a red blood cell. Solute concentration equals 0.3 moles per liter. If it is bathed in salt water, solute concentration equals 1.15 moles per liter at 25 degrees Celsius. So this is going to be similar. We're going to assume that I equals 1, but our difference in molarity now is going to be the molarity of the seawater minus the molarity within the cell, and then the rest is going to be the same, being mindful to convert our temperature into Kelvin. So this pressure is huge, 21 ATM. What's going to happen in this case is, because the concentration in the solution surrounding the cells is so much higher than it is within the cells, water is going to come rushing out of our cells, hoping to equalize the two concentrations, and the pressure that will be exerted on the cells is 21 ATM. Just giving that some context, 21 times 14, that's about 294 psi. It's not really going to work out very well. That's about 10 times the pressure in your car tires, this is going to cause a problem for our cells. The poor little guys are going to get crushed and probably die. Okay, so a related concept to osmotic pressure is the idea of reverse osmosis. So we said that if we apply a pressure equal to the osmotic pressure, we can stop movement. However, if we apply a pressure greater than the osmotic pressure, we can actually make it go back in the non-spontaneous direction. So generally, if we were to have a concentrated solution separated from a less concentrated solution, we would expect solvent to move into the concentrated solution and try and dilute it. However, if we apply a pressure greater than the osmotic pressure, then we can achieve what's called reverse osmosis, and we can actually make it go the other way. So that's kind of cool, right? So that's what we're talking about here. If you apply a pressure on the concentrated side greater than the osmotic pressure, you can make the solvent move in the non-spontaneous direction. And this will increase the amount of fresh water, and as a result, you can actually use this to purify water. So reverse osmosis problems are a little bit more complicated than some of our previous problems that we've seen involving colligative properties. And so I'm going to go through a somewhat convoluted example now. You might take a little bit of time to practice this a couple of times or look at it a couple of times just to make sure that you really understand what's going on. So the question reads, what is the reverse osmosis pressure required to purify brackish water? Brackish means slightly salty, at 20 degrees Celsius. And we're given the concentration of particles in this solution as being 0.355 moles per litre. We want to purify to drinking water that contains no more than 87 milligrams per litre of ions as sodium chloride. Now, the first thing that leaps out to me is that this concentration here is given in milligrams per litre, and I need to be working in moles per litre whenever I'm doing anything with respect to osmotic pressure. So the first thing I'm going to do is take that 87 milligrams per litre and turn it into moles per litre of sodium chloride. So I don't need to in any way modify the litres, but I do need to turn the milligrams into moles. So the first thing I do is multiply by the appropriate conversion factor to convert milligrams into grams. And then finally, I use the molar mass to convert my grams into moles. And this gives me moles per litre of sodium chloride. Now, it's important to recognize that I need to give the total ion concentration in the final drinking water. So as I get 2 moles of sodium and chloride ions, 1 mole of each, and for every 1 mole of sodium chloride dissolved, I need to recognize that my total ion concentration in this solution will actually be double this, and so will be 3 by 10 to the minus 3 moles per litre. So, as I've taken into account dissociation of my ions, for both of my solutions, I don't need to worry about the Van Hoff factor when I am applying the osmotic pressure formula. So the osmotic pressure is simply going to be the molarity of my slightly salty water minus the molarity of my drinkable water times by R and then times by the temperature expressed in Kelvin. So this gives me a pressure of 8.47 atm. So as long as I apply a pressure greater than that, then I will achieve reverse osmosis. And that's a pretty standard reverse osmosis problem where we just have to do a little bit of extra math and then phrase our answer correctly. Okay, so that concludes the section on our final colligative property, which is osmotic pressure. One of the most common ways of using a colligative property is to determine the molar mass of a solute. This is normally done for either boiling point elevation, freezing point depression, or osmotic pressure. I've never seen it done for vapor pressure lowering. So this is good news for us because boiling point elevation and freezing point depression have very similar formulas. So we really only have to worry about two things. We have to figure out how we can determine the molar mass using either boiling point elevation data or freezing point depression data, or we have to figure out how to use the osmotic pressure equation to get the molar mass. So typically what will happen is this. We will dissolve a known mass of solute in a given volume of solvent and observe the effect on a colligative property. This works the best when we have a compound that we know is a non-electrolyte, because then we don't have to worry about figuring out what I is, and we can assume that I is just equal to 1. So here's a classic example using freezing point depression. We would do the same math if we used boiling point elevation. It says 100 milligrams of a non-electrolyte was dissolved in 1 gram of benzene, and the freezing point depression constant of benzene is 4.9 degrees Celsius per mole. The freezing point of this solution was 1.75 degrees Celsius lower than for pure benzene. What is the molar mass of, and this compound I guess is called ecosene. So here's our little formula. The change in freezing point is equal to Kf multiplied by the molality. Now we have the change in freezing point and we have Kf, so let's go ahead and calculate the molality. So change in freezing point over Kf gives us the molality. Now we want to remember that the molality is simply equal to the moles of solute divided by the kilograms of solvent, and we can easily get the kilograms of solvent, so that means that we can solve for the moles of solute. So the moles of solute is simply going to be our molality, which we just got, multiplied by our kilograms of solvent. I do need to be mindful to convert my grams of benzene into kilograms of benzene. But having done that, I can now get my moles of my solute, which is called ecosene in this case. The final step is pretty easy. To get the molar mass, we have to remember that the molar mass is the mass in grams divided by the moles, and we were told that we dissolved 100 milligrams of our compound into this 1 gram of benzene. So 100 milligrams is the same as 0.1 grams, and we just figured out that we had 3.57 by 10 to the minus 4 moles. So grams over moles gives me molar mass, and the molar mass of my compound is about 280 grams per mole. So that's how we would handle data for either freezing point depression or boiling point elevation. And if you read through this a couple of times and cautiously make notes, I'm certain that you're going to be able to master these kinds of problems. The other kind of problem where we're asked to solve for the molar mass that we'll see will be concerned with using osmotic pressure data. So this one says we have 47 milligrams of a non-electrolyte, that's just telling us that I is equal to 1, was dissolved in water to give 2.5 mils of a solution at 25 degrees Celsius. The osmotic pressure of the solution was 0.489 atm. What is the molar mass of the compound? So this is a classic one where they don't mention a second solution. So the molar mass of the molarity, of our second solution just has to be assumed to equal 0. So under those situations, the osmotic pressure is equal to the molarity of our solution multiplied by the ideal gas constant multiplied by the temperature in Kelvin. We know the osmotic pressure, 0.489 atm. We know the volume of our solution, we know the grams of our solute, and we know the temperature. I think the sensible thing to do here is to reorganize the osmotic pressure equation and solve for the molarity. So the molarity will just be equal to pi over RT. So at this point, we can get the molarity. So we want to recognize that molarity is equal to the number of moles over the volume in liters. And as we have the volume, it is given in milliliters, we can solve for the number of moles. So the number of moles is just going to be equal to our molarity times by our volume. So we take our molarity that we got from the first step, multiply it by our volume expressed in liters, and that gives us our moles of solute. Now we kind of know what to do from here because molar mass is equal to grams of solute over moles of solute. We have 47 milligrams of solute, which we can easily convert to grams just by multiplying by 10 to the minus 3. And we had previously solved for the number of moles. So in this case, our molar mass ends up being 940. So really, there's just two kinds of problems. Those where we're going to use osmotic pressure data and those where we will use boiling point elevation or freezing point depression data. Either way, if you study these kinds of problems, you should be able to use a colligative property determination to figure out the molar mass of a compound. So that concludes the video for section 11.4, which is concerned with colligative properties.